Welcome to the latest in my series of videos on the spectroscopy of organic compounds. In this one, I'll be covering ultraviolet visible or UV visible spectroscopy, and I'll start with a background of the sort of information that we obtain from UV visible spectroscopy, and then I'll talk about the theory and interpretation of UV visible spectra. So first, what is a ultraviolet visible spectrum? And it's very simply a plot of absorbance versus wavelength over a given region of the electromagnetic spectrum that usually only corresponds to ultraviolet light, but can also encompass the visible range. So I will include the entire range of what you typically see in a UV visible spectrum, or what you might see. So that starts about 200 or as low as 190 nanometers. So this is wavelength in nanometers versus absorbance, or absorbance versus wavelength. And 190 nanometers, of course, is in the ultraviolet region of the electromagnetic spectrum. And the ultraviolet extends to about 400 nanometers, and then the visible region extends from 400 to 700 nanometers. So this is really the entire range of wavelengths that are covered by most UV visible spectrometers. Now, from our point of view in this course, the most important piece of information that we obtain from a UV or visible spectrum is that the wavelength of absorption in such a spectrum indicates the degree of conjugation in a substance. And so what that implies is molecules or substances that have no conjugation, that is, no conjugated pi electrons, or in some cases non-bonding electrons. By non-bonding electrons, I mean electrons in lone pairs on certain heteroatoms. Unless you have one or both of those things in a molecule, the molecule will not be UV active, which means that it will not absorb in this region of 190 to 700 nanometers. So if you take a UV visible spectrum of a compound and don't obtain any absorption in the region from 190 to 700 nanometers, that also gives us useful information, because what that implies, of course, is that there are no conjugated pi electrons or non-bonding electrons in that substance, so negative information is useful. Another use of UV visible spectroscopy is that it can be used for the identification of certain combinations of functional groups, and that's because certain combinations of conjugated functional groups have similar UV spectra in different compounds. And that's not something that we'll be using nearly as much in this course, but it can be used for that purpose. Predominantly what we'll be using UV or UV visible spectroscopy for is to determine the degree of conjugation in a substance. So now we're going to turn our attention to the theory of how exactly UV visible spectroscopy works and how we can use it more specifically. So recall from our discussion of infrared spectroscopy that the transitions that correspond to the wavelengths of infrared light are transitions between vibrational energy levels in molecules. And infrared light is significantly lower in energy than visible and ultraviolet light. So ultraviolet and visible wavelengths correspond to electronic transitions instead of vibrational transitions, and that is transitions of electrons between orbitals of different energy. Now recall from general chemistry that the most accessible, that is the lowest energy electronic transitions, are for valence electrons in atoms. And in molecules, particularly in organic molecules, those valence electrons are typically locked up in bonds unless there are lone pair electrons on certain heteroatoms. And so it's those bonding electrons or non-bonding lone pair electrons that are involved in the electronic transitions that we can observe in UV visible spectroscopy. So we can draw an energy level diagram for the most likely electronic transition as in a typical organic molecule, and it would look something like this. So we have increasing energy and the different possible energy levels for the highest energy, that's bonding and non-bonding electrons. And so in all organic compounds, we're going to have sigma bonding electrons. So we'll label that a sigma energy level for electrons in a sigma bond. And then higher than that would be pi electrons for electrons in a pi bond. Non-bonding electrons, which again we're referring to lone pair electrons on heteroatoms as non-bonding electrons. Let's label those as N. And so these are all bonding orbitals, except for the non-bonding. And for each bonding orbital, we have a corresponding antibonding orbital. And antibonding orbitals, recall, are identified with asterisks. So this is a pi antibonding orbital. And the highest energy of all are the sigma star antibonding orbitals. And so in ultraviolet and visible spectroscopy, we're going to see transitions of electrons in either non-bonding or bonding orbitals to these antibonding orbitals. Now recall, we learned in general chemistry that the energy of the transition, of electronic transition, is related to the wavelength of light absorbed by a very simple equation, and that is delta E, the difference in energy between two orbitals or energy levels, is equal to Planck's constant times the frequency of the photon of light absorbed or emitted during the transition, and that's equal to, in terms of wavelength, Planck's constant times the speed of light over the wavelength. And I'll define all of these. So H is Planck's constant, that's 6.626 times 10 to the minus 34th joules times seconds. C is the speed of light, which is approximately 3.0 times 10 to the 8th meters per second. And lambda is always wavelength, and in this case it would be in meters. So a transition, for example, of an electron from a sigma bonding orbital to a sigma star antibonding orbital will have a greater energy, a change in energy, and therefore a shorter wavelength than a transition of an electron from a pi bonding orbital to a pi star antibonding orbital. It would probably be less confusing if I were to express these energy changes with arrows. So the sigma to sigma star transition is higher in energy, and since energy and wavelength are inversely proportional, it will of course have a lower wavelength, a shorter wavelength. Whereas the pi to pi star transition is lower in energy than the sigma to sigma star transition, so it will have a longer wavelength. So let's now take a look at some specific examples of these different types of transitions and their associated ultraviolet visible spectra. So we'll start with transitions or UV spectra in molecules that have no pi or lone pair non-bonding electrons. So again, lone pair is synonymous with non-bonding for our purposes here. And a good simple example of a molecule like that would be a saturated hydrocarbon. So we'll start with a really simple one, and that would be ethane. Now, obviously, a saturated hydrocarbon like ethane has no pi electrons and has no lone pairs. So there is only one possible accessible transition for the valence electrons. The valence electrons are all bonding and they're all in sigma bonds. And so the only possible transition would be a sigma to a sigma star transition. Note the symbolism that we use for transition. So what we're talking about here is what we showed just a moment ago in our energy level diagram, is this transition, this red transition. We were taking an electron in a sigma bonding orbital, that could be any one of these sigma bonds in the molecule, and exciting it to a sigma star antibonding orbital. And so this corresponds to a fairly large change in energy. And so the wavelength, the associated wavelength, will be fairly short. And it turns out that the wavelength associated with the sigma to sigma star transition in a saturated hydrocarbon like ethane has what we call lambda max. So lambda calls the wavelength of about 135 nanometers. So a couple of things to mention here. First, the definition of lambda max. Lambda max is defined as the wavelength of maximum absorbance for a given transition. So this is the maximum of the wavelength with maximum absorbance for the sigma to sigma star transition in an ethane molecule. The other very important thing to notice here is to recall that the range that we have available in ultraviolet visible spectroscopy, the wavelength range, the abscissa in our plot of UV visible spectra, ranges from a low of about 190 nanometers, often it's around 200 nanometers, depending on the spectrometer, up to the edge of the visible spectrum, which is 700 nanometers. And so clearly, this is not going to be visible in an ultraviolet visible spectrum because the wavelength is simply too low, and that's typical of sigma to sigma star transitions. This is why compounds that do not have pi electrons or non-bonding electrons are invisible in UV visible spectra. You just simply get a flat line. So you may be asking yourself, why is UV limited to this range from 190 to 700 nanometers? And the main reason for the lower limit of 190 is that atmospheric gases, because they have sigma bonds, for example, and they have pi bonds as well, that, as we're going to see, absorb at higher wavelengths, absorb in the region below about 190 nanometers. They begin to absorb around 200 nanometers. And so if you want to get a spectrum of a molecule that absorbs only in the region below 190 nanometers, you have to exclude all the atmospheric gases. And for that reason, the wavelengths that occur below 190 nanometers are often referred to as vacuum UV. That is, they can only be observed under vacuum, excluding atmospheric gases. So this effectively limits the range of UV, the typical range of UV visible spectroscopy. So we're now ready to look at molecules that have pi electrons, and we'll do that in the second part of this video.